to thank the organizer, Professor Benido, Professor Jinky, and Professor Reyes for the invitation. And when I received the invitation, I have to decide what to talk. The title helps because it's about pattern, evolution, structure, and I want to make the natural and social work hand in hand, not as a separate thing. So you'll be seeing a system that exhibits a very exciting social behavior, and then you come to realize there are a lot of organisms have sociology. So when you understand human and then you try to understand other organisms, you can see that we can learn a lot from each other. So the second reason why I have to decide on this topic is there's one grant that can support this travel. And the grant is a collaborative grant with the biologists. So I have to do my homage to the biologists. This is the title of that research, Elucidating Functional Traits and Optimization Strategy. Optimization strategy of pathogenic fungi. Fungi that look for trouble or create trouble, and using mycelium network growth model. What you see here is wonders, and I beg to differ a bit from Prof. Winkler's talk by giving credit to the biology system as it should, and not to try to reduce it to particles and rigid rods. So I'll try to focus on a few things. Primarily, I just want to bring up this interesting point of view about biological system as a natural intelligence system. And there are a lot of dynamics that we can learn in how we manage the planet. And by learning from systems like mycelium, gives us one way of bio-inspired strategies. But being a physicist, I try to focus a bit on the growth morphology from a qualitative point of view, and probably attempt to create that complexity from growth dynamics. And finally, we will see that, like what we heard before, emergence from what appears to be random behavior, but some way, you see that there is the emergence of collective phenomena, and that brings us to social biosystem. So now, I think we are all familiar with mushrooms, all sort of mushrooms. I hope there will be mushrooms during lunch. And you can find it around. If anything decays, probably inside here there is element of this. Anywhere you can see. And some are, widely used. Like the first one is oyster mushroom and lindsay. And there's a brown rod fungi is the one that keeps the place tidy. Otherwise, we'll be living in our backyard or full of waste products. So it has a lot of functions, but this is mushroom. And this is not what I'm going to talk. I'm going to talk about the mycelium. So mushroom is actually the fruit. So we are not interested with the fruit. We are interested the system that produced this fruit. And the system is the mycelium network. And if it fruits, it will produce the fruiting body. And this is the system that we are interested. And it has very interesting life cycle. It starts from the spores, germinates, and create a complex, I should use this, right? Yeah, mycelium network, and then the fruiting body, and the cycle continues. And this is a very diverse time and land scale involved. And what we'll be focusing is the mycelium here. And in particular, this is the hyphae network. And this object is actually a hyphae network and a small micro unit of this. And then it comes to cellular biology. So you can have mycelium that extends to hundreds of kilometers. It can go very far under the town. And it has a very delicate network structures. And then if you try to reduce it to the network, and it can go from kilometers to millimeter, sub-millimeter, and then sub-millimeter to sub-micron, of course, at the cellular level. And all these work together. It's very hard to separate them. Okay, and that creates a challenge to model the system. And an interesting point about mycelium is itself is a superorganism that encompasses the various aspects of dynamics, social dynamics, biological dynamics, physical dynamics. It trades, so it's a trader. It trades nutrients from the soil, from the plants, and share with other species as well. If you can have a handshake, otherwise you have to go into a war mode to take over another organism. It has a lot of sensory systems and the foraging behavior, as well as sensing the environment, seeking space, and when things become hostile or survival matters, then there is the act of, like any organism does. And then sensing, to sense whether it's a friend or foe, looking for space, communication, long distance communication between species, that can work for miles across, and many, many other behaviors. And that's what makes fungi interesting, and the mycelium in particular, amazing system. So being a physicist, sometimes when you talk to biologists, they will say that, well, you cannot reduce it to small systems that you can model by equation. So actually, we tend to agree, and we try to be faithful to that demand where possible. But again, I would like to just cover a rather introductory material here. So mycelium is also used as a model for recycling because it is a natural system that recycles the whole planet. And this is another version of WWW, that is the Wood Wide Web that connects plants. And you can see that there are a lot of effort to map a mycelium network on the underground network. No doubt it's a very challenging task. How are you going to do your tracing? It's a very challenging task, but that makes it interesting. So I'll focus on growth morphology. This is a qualitative side of the talk. The idea is to look at the macro scale, the large scale of this object. You can see this by naked eye. If you look at the petri dish and the growth of this mycelium. And second is a mesoscale to look at the networking behavior. The macro scale most often focus on the biomass, how we translate that biological, physical biomass into a digital map. That also comes with a cost that you have to do a lot of reduction. And then the network, the structure of this network. And when you focus on the network essentially a hyphae network. And how does the hyphae grow also of importance. So there are a lot of scales, but we try to break it into these three major scales. So this part will focus on two aspects. That is the spatial biomass growth taken here from the petri dish. So this is the mycelium, not the fruiting body. I'm just putting that the species that comes here is from Lindsay. And this is what you will see if you buy Lindsay. But then when you grow this in a petri dish, it's like a cloud of a whitish network, which is the biomass. Okay, and if you take this image under the microscope, you can also see this network structure appearing and growing. And this is what you see when it's growing and become saturated in this point. Okay, so I'll focus on these two using some of the models that we probably are familiar with, and see how this can be even further explored. So first, the experiment on mycelium, we obtained this from the biologist, and we tell them what to grow, but then they will tell us, we cannot grow that way. So let's grow the way mycelia are grown. taken from the source and then replanted on a petri dish with a different algal growth media. So we will show you for 3 types of growth media. That is the agarose of the least nutrient. And this is of 1 order of nutrient, and we cut that nutrient level to half. So this will be 3 different types of growth to study the growth rate. And then we observe this under the microscope, or even naked eye, you can see the large structure. But for the network, you need to use the microscope and observe this over time and try to understand the pattern. Okay, so what you see is after you perform some simple imaging and image pre-processing, what you can see is agarose, the least nutrient, and this is the full nutrient. And if you cut down the food by half, there's a structural change, and this is a half nutrient. Okay, so day 1, you observe over many days, but I'll show you here for day 1, 3, 5, 7, and this is a structure. So what we want to know is the space filling property, the growth front. How does the front growth? Is it possible to model this? And also to match with other systems. So this is basically covered very fast, but you see a very high branching level. This is in between, intermediate behavior. Okay, so far seems like consistent, but we will see that there are a lot of intricate things that happens. So if you are familiar with the fractal analysis, it's basically a space filling. When it comes to 2D area, if you take the front, it's just the front, and that would be the growth front. And this growth front is again space filling, but more interesting feature is the regularity of the front. If it's close to a Euclidean object, you will have a very regular front, smooth fronts. In this case, if you have a Euclidean area, the filling will be very much, all area filling, 2-dimensional filling, that is a dimension 2. So you can estimate the space filling characteristic by doing a simple scaling law of the counting. By changing the size of the boxes, you can calculate the space filling property and perform over a number of scales. And the scaling laws can be used to determine the space filling or regularity of the growth front. So these are the very simple analysis that you can do, and you can teach this to anyone, even at school. You bring a graph paper and give it to the kids, they can just catch the pattern and reveal the geometric feature of the objects. So the interesting part here is there is a law called area parameter. There is a relationship between the area fractal and the perimeter fractal. And the scaling law is quite ubiquitous. You can see it in many different systems, including expansion of bacteria colony, in township, how does the town evolve and expands, and connecting these 2 parameters, it is possible to come up with another measure called the allometric. It's actually proportionality. How does, how tall, how big you will be, what is the surface area of the body, and so on. So there is a certain sense of finiteness that you can have. So if it's a non-fractal objects, perimeter dimension 1, and then the area dimension 2, you're supposed to approach 0.5. So these are simple analyses that you can do. And we did this for the objects that you saw, the fractal of perimeter fractal, and then the area fractal, then allometry. 0.5 is the ideal growth, but anything other than that is exhibit a fractal growth with a lot of area exploring foraging strategy. But it's not good enough yet. We need to look at the other possibilities of characterizing these objects. For example, this is the radial growth. Choose the origin at the inoculation point, and then determine the radius to the front. And this object itself can be treated as a random process, just like any front growth. For example, the KPZ equation can be used to study how does the front propagates. So this is again, you can apply stochastic model for the growth front. And the growth rate of this object, you can see for the least nutrient is very much stagnated. So these are a few analyses that one can do, and biologists are quite happy with this because that helps. But then again, there are models that people have introduced. Some of our earlier work on Brownian motion and scale Brownian motion seems to be applicable here. When you actually play with their time, basically time is fixed. Time graduate is fixed, 1 second, 2 seconds, 3 seconds. But you can make that time evolution nonlinear. Why keep it in linear? If you go fast, you can accelerate the time or you can dilate the time. So this scale Brownian motion essentially is a scaling the time. So you expedite the time evolution or you slow it down, depends on your exponent here. And it can go by time scaling as well, not necessarily fixed. And this has been used for a variety of systems, and a model actually governed by this Langevin equation. And what's important here is to model the growth front using the SBM. This is one aspect that we can look at. And the time scaling parameter here, the diffusion, time-dependent diffusion constant, can now be used as means to characterize the dynamics. Yes, yeah, got it. Okay, so next is the complex network analysis. What we do is we perform image segmentation to obtain a complex structure from here to here. And this is not trivial because what you see as a very whitish, cloudy image here actually needs to be, you have to do a lot of image processing in that sense. So I'll skip this part, but this is what one can do. It's taking this picture, performing image reduction, and then segment this to form a network, and then the node and the edges can be characterized to obtain the agency matrix. And this matrix is used in complex network analysis to determine various properties, such as the clustering coefficient. Okay, so I'll speed up a bit here just to highlight, because I would like to go to the next part on the dynamics just quickly. So this is again for the oyster mushroom observed under different time, reduced, and this is the evolution in network. And this network obtained as a node and edges. Once you get these, the agency matrix can be obtained. From that, you can calculate the eigenvalues. The eigenvalues, the first one talks about connectivity. The second part is the clustering or community detection. So this is for the time that you see. So it is possible to look for various, structure in the graph for the system. So this is interesting part. When you say it explore, the way it explores, the branching behavior become very complicated from very, it's like a baby hair here, but then it has a lot of branching appearing at this part. Okay? So there are a lot of dynamics that happen. It's not just simple lack of food. The way you forage is important. And there are many models that's been introduced as well based on guerrilla warfare or the phalanx way of marching forward in different, in a kind of coherence. So just to give you a flavor, there are a lot of, strategy involved. And this is two different species put together, and you observe it over time, and they come close, and they are not in any confrontation. One will just take over the other, grow over, okay? So this is quite important, but there are more to it. You can have confrontational. This is a deadlock fighting for space, overtake, and then this is, happy marriage or something, then they actually have a fruiting body. So you can have a lot of things, all right? So growth dynamic is interesting because now at the hyper level, you can model this using a rate equation. This is tiny a bit. This is due to Falconer. You look at the resource. This is the dead body that no longer participate. This is an immobile but participate in transferring the biomass. And this is mobile biomass, biomass that moves from places to places. And this term is about recycling strategy. And this is inhibition. This is the crisis management equation. So if you solve this all by numerical, it is possible to get, the dynamical pattern of the growth. But then again, you can use very simple strategy as well. This is a very, very simple model. Okay? This is very simple model. You can see it's just you have a random velocity, and then you have an L system. This is the L system, and you can still create a complex dynamics. So it's a kind of, a decision whether you want to use a very detailed mass transport equation to create the feature, or you can use some kind of geometrical rule base to create this feature. And then you calculate the properties that you observe and then see whether it captures the dynamics. Okay? And more complex phenomena can be seen if you can track these particles inside the hyphae, which is a very challenging task. We don't have the facility to do this in our university, but then, it can be modeled by, this is a rate equation. How does a particle combine and then form an intermediate, and then when it goes to the end of the hyphae tip, it can actually form the structure of the body. Okay, I'll skip this. Finally, the statement is, mycelia basically act like a mother in the forest, and in some cases, it also acts as a very hostile member of the community. So it all depends what it wants. But this book is very interesting. In forests, there are trees that actually serve as a mother, but the real worker are the root system, the mycorrhizal, and the mycorrhizal fungi. Okay, so I'll finish this with a word of thanks to the organizer for the invitation and the collaborators from the biologists. So when you actually work together and you collaborate, and there could be a possibility for fruiting interesting ideas. But then if you are hostile between a species, and then things won't work out, one will try to overtake the other and rule. Actually, we see this in real life, but it also happens in mycology. Okay, so I hope I've given you a very general fly-through of this qualitative behavior. End of the day, it's complex system. You can find a model to describe it, but end of the day, you take away something of that amazing features of the biological systems that probably requires a different paradigm in modeling. And that may not be just plain, gray or black and white of dynamical equations. There could be a lot of sociology involved, and there are a lot of rooms to explore when we collaborate with sociologists and also even from people from the other discipline. Okay, thank you very much then. Thank you.